Welcome to the lesson on Euclid's division lemma. At the end of this lesson, you will be able to state the principle of Euclid's division lemma and calculate the highest common factor of any two positive integers by applying Euclid's division lemma. You will also be able to identify certain properties of numbers by applying Euclid's division lemma. Meet Mr. Chatura. He runs a stationery shop. To keep a track of all the items in his shop, he uses a special form. Right now, he's checking his stock. Let's take a closer look at his form. The first column of this table shows the names of different items Mr. Chatura sells. The second column shows the number of items in standard boxes available. Now, let's follow Mr. Chatura as he fills his table. Each box of pencils has 12 pencils, and Mr. Chatura has 5 such boxes. This means that there are 60 pencils in the boxes. He also has 3 extra pencils. Thus, the total number of pencils is 63. Each box of erasers has 10 erasers, and Mr. Chatura has 8 such boxes. This means that there are 80 erasers in the boxes. He also has 6 extra erasers. Thus, the total number of erasers he has is 86. Each box of sharpeners has 8 sharpeners, and Mr. Chatura has 4 such boxes. This means that there are 32 sharpeners in the boxes. He does not have any additional sharpeners. Thus, the total number of sharpeners is 32. Each box of ballpoint pens has 15 pens. But right now, Mr. Chatura doesn't have a complete box. He has 10 extra ballpoint pens. Thus, the total number of ballpoint pens he has is 10. Now pay attention to the values in each row of the table. In the first row, the total 63 is equal to 12 multiplied by 5 plus 3. Similarly, in the second row, 86 is equal to 10 multiplied by 8 plus 6. The last two rows are interesting. In the third row, we can say 32 is equal to 8 multiplied by 4 plus 0. Similarly, in the fourth row, 10 is equal to 15 multiplied by 0 plus 10. Now, let us come to the point. If we assign labels to the values in the different columns of the table, we can see that they all follow a general relation. The total A is equal to the pieces per box, B, multiplied by the number of boxes, Q, plus additional items, R. This relation is known as Euclid's division lemma, which states that for any two positive integers, A and B, we can find two whole numbers, Q and R, such that A is equal to B multiplied by Q plus R. From Mr. Chatura's table, you can see that Euclid's division lemma holds true even if either Q or R is 0. Now suppose Mr. Chatura discovers he has 12 extra pencils instead of 3. What happens to Euclid's division lemma in this case? 12 pencils add up to one complete box. So we see that if R becomes equal to B, the value of Q increases by 1 and the value of R is reduced to 0. Thus, the value of R in the equation for Euclid's division lemma can be greater than or equal to 0 and less than the value of B. Mr. Chatura has got a fresh stock of pencils and erasers. He is making space to arrange them on the shelves. Mr. Chatura has got 520 boxes of pencils and 140 boxes of erasers. He wants to arrange them in the least number of shelves, such that each shelf has an equal number of boxes of pencils and an equal number of boxes of erasers. Mr. Chatura has figured out a solution. All he has to do is find the highest common factor, or HCF, of 520 and 140. Now, how does he do that? Mr. Chatura can use Euclid's division lemma to find the HCF of 520 and 140. Let's see how. Let's apply Euclid's division lemma to the two numbers taking the larger number equal to A and the smaller number equal to B. Dividing 520 by 140, we see that 140 goes into 520 3 times and leaves a remainder of 100. Now consider the value of B and R in this equation. We see that R is not 0. So let's apply Euclid's division lemma, taking 140 as A and 100 as B. Dividing 140 by 100, we see that 100 goes into 140 once and leaves a remainder of 40. Now consider the values of b and r in this equation. We see that r is not 0. So let's apply Euclid's division lemma, taking 100 as a and 40 as b. Dividing 100 by 40, we see that 40 goes into 100 two times and leaves a remainder of 20. Now consider the values of b and r in this equation. We see that r is still not 0. So let's apply Euclid's division lemma, taking 40 as a and 20 as b. Dividing 40 by 20, we see that the 20 goes into 42 times and leaves a remainder of 0. Note that in this equation, the value of r has become 0. The value of b in this case, that is 20, which is the HCF of the numbers 520 and 140. By Euclid's division lemma, we found that HCF of 520 and 140 is 20. Thus, Mr. Chatura can arrange his stock in 20 shelves, each having 26 boxes of pencils and 7 boxes of erasers. Now, let's observe the process of finding the HCF of any two given positive integers using Euclid's division lemma. Suppose we have two positive integers, a and b, such that a is greater than b. Apply Euclid's division lemma to the given integers a and b to find two whole numbers q and r, such that a is equal to b multiplied by q plus r. Check the value of r if r is equal to 0. Then, b is the HCF of the given numbers. If r is not equal to 0, apply Euclid's division lemma to the new divisor b and the remainder r. Continue this process till the remainder r becomes 0. The value of the divisor b in that case is the HCF of the two given numbers. Euclid's division algorithm can also be used to find some common properties of numbers. Let's take this problem to show that every positive odd integer is of the form 2q plus 1. Let a be any positive odd integer. Then, by Euclid's division lemma, we can write a is equal to b multiplied by q plus r. If we take the value of b as 2, we can write a is equal to 2 multiplied by q plus r. By Euclid's division lemma, the value of r can be greater than or equal to 0 and less than b. Since b is equal to 2, the possible values of r are 0 and 1. Putting in the values of r as either 0 or 1, we get the possible values of a as either 2q or 2q plus 1. Now the value of a cannot be 2q, since 2q is divisible by 2 and a is an odd integer. Thus we can say that any positive odd integer can be of the form 2q plus 1. You've reached the end of this section. Let's have a quick recap of the key points covered in this section. Recall that Euclid's division lemma states that for any two positive integers a and b, we can find two whole numbers q and r, such that a is equal to bq plus r, where r is greater than or equal to 0 and less than b. Euclid's division lemma can be used to find the highest common factor of any two positive integers. It can also be used to show the common properties of numbers. You can now proceed to the next section. Hope you enjoyed this learning experience. Welcome to the lesson on the fundamental theorem of arithmetic. At the end of this lesson, you will be able to state the fundamental theorem of arithmetic. You will also be able to apply the fundamental theorem of arithmetic to calculate the prime factors, the HCF, and the LCM of any two composite numbers. Meet Mr. Number Maker. He's an old vagabond who's always on the move, but he has a special skill. Mr. Number Maker claims that he can produce any composite number you can think of. He uses a special set of tools to do so. Let us take a look at these tools. Oh, so Mr. Number Maker's tools are just a set of numbers. But these numbers are special. Observe carefully. What kind of numbers are these? All these are prime numbers. In fact, Mr. Number Maker has an infinite collection of all the prime numbers in his magical suitcase. Let's verify Mr. Number Maker's claim. Let's take a number. Any number. Say 1950, the year India adopted its constitution. Now, let's create a factor tree for this number using Mr. Number Maker's tools. Dividing 1950 by 2, we get 975. Dividing 975 by 5, we get 195. Dividing 195 by 5 again, we get 39. Dividing 39 by 3, we get 13. Now, 13 itself is a prime number, so we cannot factorize it any further. Thus, we see that 1950 can be expressed as a product of 2, 5, 5, 3, and 13, each being a prime number. What is true for 1950 is true for any composite number you can think of. Mr. Number Maker's claim is based on the fundamental theorem of arithmetic that states every composite number can be expressed or factorized as a product of prime numbers. Is there any other way to factorize 1950 using prime numbers? Let us see. Starting with 5 instead of 2, we get another set of prime factors for 1950. How are these factors different from the earlier ones? Note that the set of prime factors for 1950 still remains the same. Only the order of the prime factors has changed. This brings us to the complete statement of the fundamental theorem of arithmetic that states that every composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique except in the order of prime factors. We can write the prime factorization of a number in the form of powers of its prime factors. Let us see how this is done. This is how it is done. Since 5 occurs twice in the prime factorization of 1050, its power is 2. Since 2, 3 and 13 occur once in the prime factorization of 1950, their power is 1. Mr. Number Maker has another interesting tip for you. He says that by expressing any two numbers as the product of their prime factors, you can easily calculate their highest common factor, that is, the HCF, and the lowest common multiple, that is, the LCM. Now, let us see how this is done. Let's put Mr. Number Maker's tip to use. We already have the prime factorization of 1950. Now, let's take another number, say 2010, the year India hosts the Commonwealth Games. Let's find the prime factorization of 2010. Dividing 2010 by 2, we get 1005. Dividing 1005 by 5, we get 201. Dividing 201 by 3, we get 67, which itself is a prime number. Thus we see that 2010 can be expressed as a product of 2, 5, 3, and 67, each being a prime number. Since all the prime factors of 2010 appear once in its prime factorization, the power of each of them is 1. Now, let us consider the prime factorization of 1950 and 2010 together. Let us first find the highest common factor, or HCF, of these two numbers. To find the HCF of the two given numbers, locate the common factors in their prime factorization. 2, 3, and 5 are the common factors in the prime factorization of 1950 and 2010. Next, find the product of the terms containing the least powers of common prime factors of the two numbers. Let's see what this means. Since the powers of common factors 2 and 3 are 1 in both the cases, their power will remain 1 while calculating the HCF. The powers of common factor 5 in the prime factorization of 1950 and 2010 are 2 and 1 respectively. We will use the power 1 in calculating the HCF since it's the smallest power of 5. Thus, the HCF of the given numbers is 2 into 3 into 5 or 30. Now, let us first find the least common multiple, or LCM, of these two numbers. The LCM of two numbers is given by the product of the terms containing the greatest power of all prime factors of the two numbers. Since the greatest power of the common factors 2 and 3 are 1 in both the cases, their power will remain 1 while calculating the LCM. The power of common factor 5 in the prime factorization of 1950 and 2010 is 2 and 1 respectively. We will use the power of 2 in calculating the LCM since 2 is the greatest power of 5. The remaining prime factors 13 and 67 is the prime factorization of the two numbers who appear in the power of 1 in the LCM. Thus, the LCM of the given numbers is 2 into 3 into 5 square into 13 into 67, or 1,30,650. By now, we have expressed two randomly selected numbers as products of prime numbers. We have also used their prime factorization to calculate their HCF and LCM. Now, let us look at another interesting relation. Let us find the product of 1950 and 2010. First, let us find the product of the HCF and LCM of the given numbers. What do you observe? Note that the product of the given numbers is equal to the product of their HCF and LCM. This result is true for all positive integers and is often used to find the HCF of two given numbers if their LCM is given and vice versa. You've reached the end of this section. In this section, you learnt about the fundamental theorem of arithmetic. The theorem states that every composite number can be expressed or factorized as a product of prime numbers, and this factorization is unique except in the order of prime factors. You have also learned that the HCF of two numbers is equal to the product of the terms containing the least powers of the common prime factors of the two numbers. The LCM of the two numbers is equal to the product of the terms containing the greatest powers of all prime factors of the two numbers. And the product of two positive integers is equal to the product of their HCF and LCM. Welcome to the lesson on revisiting rational and irrational numbers. At the end of this lesson, you will be able to distinguish between rational and irrational numbers. You will also be able to prove theorems related to rational and irrational numbers. There is a big commotion at the Rational Numbers Club. The club is exclusively for rational numbers, but it appears some trespassers have gotten inside. It seems the rational numbers have identified the trespassers as irrational numbers, but the trespassers insist they too are rational numbers. This debate is really getting heated. Well, the law of Numberland has taken its course, and the accused trespassers have been summoned in court. The accused still insist they are rational numbers. Here is Mr. Public Prosecutor, who believes that the accused are irrational and not rational numbers. Let us see how he presents his case. Mr. Public Prosecutor is kind enough to present his notes on this screen for all of us to see. Mr. Public Prosecutor is starting by introducing the two parties to the case. A number is called rational if it can be written in the form P upon Q, where P and Q are integers and Q is not equal to 0. A number is called irrational if it cannot be written in the form of P upon Q, where P and Q are integers and Q is not equal to 0. The accused still stand by their claim of being rational numbers, but Mr. Public Prosecutor is all set to begin his argument. Let us hear what he has to say. The theorem Mr. Public Prosecutor wants to present states that if a prime number P divides Q square, then P also divides Q, where Q is a positive integer. To prove the theorem, let us assume that Q is a positive integer whose prime factors are P1, P2, P3 to Pn, not necessarily distinct. Thus, Q square is equal to the product of the squares of P1, P2, P3 to Pn. It is given that the prime number P divides Q square. By the fundamental theorem of arithmetic, Q square has a set of unique prime factors P1, P2, P3 to Pn. Thus, P is one of the prime factors of P1, P2, P3 to Pn. But P is also a factor of Q. Thus, we can say that if a prime number P divides Q square, then P also divides Q, where Q is a positive integer. Where is this argument heading? Is Mr. Public Prosecutor accepting that square root of 2 is a rational number? If we assume square root of 2 is a rational number, then by definition, two integers must exist, P and Q, where Q is not equal to 0, such that square root of 2 is equal to P upon Q. Now, suppose P and Q have a common factor, R, other than 1. Dividing both P and Q by R, we get root 2 equal to A by B, such that A and B are two co-prime integers. This means that A and B have no common factors other than 1. In this condition, a rational number is said to be in its standard form. So, we have square root of 2 equal to A by B. Squaring both the sides and rearranging the equation, we get 2 times B square is equal to A square. This means 2 divides A square. Since 2 divides A square by the earlier theorem, we proved that 2 divides A. Thus, we can also say that A is equal to 2 times C for an integer C. Putting the value A is equal to 2 times C in the previous equation for A and B, we get 2 times C square is equal to B square. This means 2 divides B square. Since 2 divides B square by the earlier theorem, we proved that 2 divides B. Now, wait a minute, there's a contradiction here. Since 2 divides both A and B, it is a common factor of A and B. This contradicts the fact that A and B are co-prime numbers and have no common factors other than 1. This contradiction has arisen because of our first assumption that square root of 2 is a rational number. Hence, saying square root of 2 is a rational number is incorrect. Thus, Mr. Public Prosecutor has proven that square root of 2 is an irrational number. Let us see if square root of 3 can satisfy the condition of being a rational number. If we assume square root of 3 is a rational number, then by definition, two integers must exist, p and q, where q is not equal to 0, such that the square root of 3 is equal to p upon q. As before, suppose p and q have a common factor r other than 1. Dividing both p and q by r, we get square root of 3 equal to a by b, such that a and b are two co-prime integers. This means that a and b have no common factor other than 1. So, we have square root of 3 is equal to a by b. Squaring both sides and rearranging the equation, we get 3 times b square is equal to a square. This means 3 divides a square. Since 3 divides a square by the earlier theorem we proved, we can say that 3 divides a. Thus we can also say that a is equal to 3c for some integer c. Putting the value a is equal to 3c in the previous equation for a and b, we get 3 times c square is equal to b square. This means 3 divides b square. Since 3 divides b square by the earlier theorem we proved that 3 divides b. So we arrive at the same contradiction. Since 3 divides both a and b, it is a common factor of a and b. This contradicts the fact that a and b are co-prime and have no common factor other than 1. This contradiction has arisen because of our first assumption that square root of 3 is a rational number. So, saying square root of 3 is a rational number is incorrect. Mr. Public Prosecutor has thus proven that square root of 3 is also an irrational number. Now, let us see if 2 plus square root of 3, which is the sum of a rational and irrational number, is a rational or irrational number. If we assume 2 plus square root of 3 is a rational number, then by definition, there must exist two co-prime integers, a and b, where b is not equal to 0, such that 2 plus square root of 3 is equal to a by b. Rearranging the equation, we get square root of 3 is equal to a minus 2b upon b. This is a rational number, since a and b are both integers. We again face a contradiction here. The equation here shows that square root of 3 is equal to a rational number. This contradicts that square root of 3 is an irrational number. We have already proven this. This contradiction has arisen because of our first assumption that 2 plus square root of 3 is a rational number is incorrect. Mr. Public Prosecutor has thus proven that 2 plus square root of 3 is also an irrational number. The judge's verdict has arrived. It says that a number that cannot be written in the form a upon b, where a and b are integers and b is not equal to 0, are called irrational numbers. The verdict further says that the sum, the difference, the product, or the quotient of a rational and an irrational number is also an irrational number. The irrational numbers have accepted they are different, but they now allege that all the rational numbers are also not the same. What are they hinting at? The judge has asked the public prosecutor to intervene. Let us hear what he has to say. On this issue, Mr. Public Prosecutor seems to agree with the irrational numbers. According to him, the rational numbers are of two different kinds. Let us look at a few examples of rational numbers to see how they are different. The decimal form of the rational number 3 by 8 terminates or has a finite number of digits. The decimal form of the rational number 5 by 3 does not terminate. It has an infinite number of digits and is a recurring decimal number. The decimal form of the rational number 16 by 25 terminates or has a finite number of digits. The decimal form of the rational number 7 by 11 does not terminate. It has an infinite number of digits and is a recurring decimal number. Thus we see that rational numbers are of two types depending on whether their decimal form is terminating or recurring. If a rational number is not expressed in its decimal form, is there any way to tell whether its decimal expansion terminates or not? Let us see what is so special about the rational numbers whose decimal expansion terminates. Do you notice a pattern when we express these rational numbers in a decimal form? Note that for all these rational numbers whose decimal expansions terminate, the prime factorization of the denominator has the power of 2 or 5 or both. Mr. Public Prosecutor has introduced a theorem that says that if P upon Q is a rational number such that the prime factorization of Q is of the form 2 raised to the power of A into 5 raised to the power of B, where A and B are positive integers, then the decimal expansion of the rational number P upon Q terminates. Does this theorem in any way apply to rational numbers written as terminating decimals? Here are some rational numbers which are terminating decimals. Let us see what Mr. Public Prosecutor intends to do with them. Let us write all these terminating decimals as rational numbers of the form P upon Q. Note that for all these rational numbers, the prime factorization of the denominator has power of only 2 or 5 or both. Mr. Public Prosecutor has introduced another theorem that says that if a rational number is a terminating decimal, it can be written in the form P upon Q, where P and Q are co-prime, and the prime factorization of Q is of the form 2 raised to the power of A into 5 raised to the power of B, where A and B are positive integers. So, how can you identify a rational number whose decimal expansion does not terminate or is recurring? Mr. Public Prosecutor seems to have a theorem for this also. Mr. Public Prosecutor has introduced another theorem that says that if P upon Q is a rational number such that the prime factorization of Q is not of the form 2 raised to the power of A into 5 raised to the power of B, where A and B are positive integers, then the decimal expansion of the rational number P upon Q does not terminate and is recurring. The trespassers in the Rational Numbers Club have accepted that they are irrational numbers and different from rational numbers. The rational numbers too have accepted that they are of two different kinds, that is, terminating and recurring decimal types. This seems to be heading for a happy ending. The rational and irrational numbers have decided to forget their differences and become friends. Don't you think we too can take a cue from them and live happily together? You reached the end of this section. Let's have a quick recap of the key points covered in this section. A number is called a rational number if it can be written in the form of A by B, where A and B are integers and B is not equal to 0. A number is called an irrational number if it cannot be written in the form of A by B, where A and B are integers and B is not equal to 0. The sum, difference, product, or quotient of a rational and an irrational number is also an irrational number. Rational numbers are of two types depending on whether their decimal form is terminating or recurring. If a rational number is a terminating decimal, it can be written in the form P upon Q, where P and Q are co-prime and the prime factorization of q is of the form 2 raised to the power of a into 5 raised to the power of b, where a and b are positive integers. If p upon q is a rational number such that the prime factorization of q is of the form 2 raised to the power of a into 5 raised to the power of b, where a and b are positive integers, then the decimal expansion of the rational number p upon q terminates. If p upon q is a rational number such that the prime factorization of q is not of the form 2 raised to the power of a into 5 raised to the power of b, where a and b are positive integers, then the decimal expansion of the rational number p upon q does not terminate and is recurring. You can now proceed to the next section,